Chapter 1, Homework A. Question number 1. A perfect gas is also called ideal gas. Undergo isothermal compression. Isothermal means temperature is constant, which reduce volume by 1.8, and the final pressure temperatures are all given. It asks you to calculate original pressure. So for isothermal process, constant temperature, the gas obeys Boyle's law. Okay, and so Boyle's law means P1 V1 equals P2 V2. Okay, and if you plot it, okay, it's called isotherm. So constant temperature, so the pressure volume is inversely proportional, like this. So at low volume, high pressure, at large volume, low pressure, because the product is constant. All right. Now the question is, which direction is it go to the right or to the left? Now in this case, it says the volume is reduced, so it should go to the left because the volume is becoming smaller, reduced by 1.8. Okay, so you should draw an arrow like this. Okay, so this is isotherm, and this is original pressure and the volume P1 V1, and this is the final pressure volume P2 V2. So what is given? The P2, okay, final pressure, final volume, so are all given. And for the for the final is here. For the initial condition, we know the volume reduced by 1.8. That means V1 minus V2 is 1.8. That means we can calculate V2 or V1. Okay, initial volume should equals to 1.8 plus V2. Okay, because volume is reduced, and that means the final volume is less than initial volume. So initial volume is larger than the final volume. So 1.8 plus V2. Okay, and what is asked to calculate is the P1. All right, so according to this Boyle's law, we can calculate P1 equals P2 V2 divided by V1. Okay, so you can plug in all the data. All right, so here first you need to calculate V1 is 1.8 plus V2, and that gives you 3.94 cubic decimeter. Now remember, this is a compression, volume decrease. But if the question is expansion, so then everything is opposite. So go to the right, and the volume should minus. Okay, should be V2 minus 1.8. So in this case, you get V1 and V2. Okay, you plug in here V1, and that is 3.94. Now, what about the unit? Now, unit, you don't have to be cubic meter. Remember, cubic meter is the SI unit, but because in this equation, all right, we don't need a gas constant, and as long as V1, V2 are in the same unit, okay, consistent, then that's fine. And the P1, P2 also in the same unit. So here, both volume are cubic decimeter, so the unit will cancel. And the P1, we use Torr, and therefore the final pressure, final answer for P1 is also in Torr. So that's question A. Okay. Now B asks you in bar. So what is the relation between Torr and the bar? Okay, one relation is think about atmosphere. So 1 atmosphere we know equals 760 millimeter mercury height, and millimeter mercury height is Torr. All right. We also know it is 1.03 times 10 to the 5th Pascal. Okay. It's also so also we know it equals and 1 bar equals 1 times 10 to the 5th Pascal. Okay, so using this, we can find the relation. And so this is the Torr. Okay, you write the conversion factor. Torr, all right, 1 atmosphere equals 760 Torr. Okay, so Torr cancel, so you get atmosphere. All right, and then 1 atmosphere is 1.013 bar. So 1 atmosphere is this Pascal, so 1 bar is this, so that relation is 1 atmosphere is 1.013 bar. And so cancel atmosphere, you get bar. All right, so the answer is 1.07 bar. All right, that's question 1. Question number 2. A homeowner uses 4 times 10 to the 3rd power cubic meter, that's the volume of natural gas, in a year to heat a home. Assume the gas is ideal gas or perfect gas, means that it obeys ideal gas law. All right, so PV equals nRT. The pressure is 1 atmosphere, temperature is 20 Celsius. It asks you to calculate the mass of the gas used. Now, if we look at the ideal gas law, so what is given is the volume, pressure, and the temperature. Okay, it asks you to calculate the mass. So from this ideal gas law, we can calculate number of moles, and then we use molar mass times number of moles. We can calculate the mass of the gas. So first, we need to calculate the number of moles. Okay. Now, when you use this equation, we need to choose a correct R constant. In this case, question, pressure is atmosphere, volume is cubic meter. Okay. So there's several ways we can do. One, we can keep pressure atmosphere, and volume we change cubic meter to liter, and then the gas constant is 0.082. All right. So this R constant is when the pressure is atmosphere, volume is liter. So that's one way to do it. Or we can keep cubic meter, that's a SI unit, and change atmosphere to Pascal. So everything is SI unit. Then the R constant is 8.314. Okay, that's when everything is SI unit. And also, in any case, the temperature must be in Kelvin. So Celsius change to Kelvin first. Okay, so here is given, and use ideal gas law. So number of moles is calculated by PV divided by RT. So here we change atmosphere to Pascal. The unit conversion factor is 1.013 times 10 to the 5th Pascal per atmosphere. Okay, and volume you keep cubic meter SI unit, and R is 8.3145, and temperature 20 Celsius plus 273.15 Kelvin, that give you Kelvin. Okay, so calculate the number of moles is 1.66 times 10 to the 5th mole. And then what is the molar mass? Okay, carbon is 12, hydrogen is 1 times 4, that give you around 16. So use 1604 gram per mole, all right, times number of moles. That give you grams, which you can change to kilogram. Okay. Question number 3. A balloon filled with 10.5 liter of argon at 18 Celsius and 1 atmosphere rise to a height in the atmosphere where the pressure is 248 torr and temperature is negative 30.5. What is the final volume and balloon? Now this question is about state change. So it changed from state 1, which has volume 10.5 and temperature T1, 18 Celsius, the pressure P1, 1 atmosphere, goes to P2, 248 torr, temperature T2, negative 30.5 Celsius. Okay, you need to change to Kelvin. So we want to calculate volume V2. So obviously a combined gas law would work. So in this case, the V1, T1, P1 are all given, P2, T2 are given. So we want to calculate V2, so P2. And modify the equation. Again, the unit has to be consistent. So P1, P2, so P1 is 1 atmosphere. P2 is 248 torr. This must change. Either change both to atmosphere or change to torr. So here we change 1 atmosphere equals 760 millimeter mercury height or torr over T1. T1 is 248. T2 P2 is 248 torr. And temperature, you need to add 273.15 Kelvin. So T2 is minus 30.5 Celsius plus 273.15, and T1 is 273.15 plus 18, and then times volume V1 for 10.5 liter, and the answer will be 26.8. Question number 4. This is a mixture. It contains hydrogen 1 gram, oxygen 1 gram. In a container, volume is given and temperature is given. So temperature. It asks you assume each gas behave as ideal gas. Calculate the partial pressure, total pressure, composition. Okay. So for a mixture, whenever we want to calculate the pressure, either total pressure, partial pressure, we must change grams to moles. So first, calculate number of moles of oxygen, number of moles of hydrogen. So if this is 1, this will be 2. Okay, so calculate moles. How do you calculate moles? You use grams divided by molar mass. Okay, mass divided by molar mass give you number of moles. And to calculate pressure, because everything is ideal gas, so we have 2 ways to do it. One is calculate total pressure, total number of moles use ideal gas law, or you can calculate partial pressure first. Okay, so here calculate the moles, all right, and calculate the partial pressure. It's just like the sample question in the lecture notes. So for hydrogen, number of moles, RT divided by volume. For oxygen, is number of moles oxygen, RT, as if there's no hydrogen. All right, you get the partial pressure, and then add together, give you total pressure. To calculate the composition, you use moles divided by total number of moles. Okay, now the moles divided by total number of moles, this is a mole fraction, but it asks you in mole percent. So mole percent, then you need to times 100%. Okay, so this is a mole fraction times 100, add the percentage. So the answer is 94.1%. Similarly, oxygen, you should get 5.9%. Question 5. A balloon contains 2 moles hydrogen, 1 mole nitrogen, 2 more helium at 273 Kelvin. Calculate the mole fraction and their partial pressure. So note that this question doesn't say everything behave as ideal gas. Okay, so you cannot use ideal gas law for this case. All right, and we know number of moles, and we can calculate mole fraction for each of them. And to calculate partial pressure, we know this equation that the partial pressure equals total pressure times mole fraction. Okay, I means certain gas. All right, so we need to know what is the total pressure. Now, for a balloon in the air, we know that the pressure inside the balloon must equal to the pressure outside. And outside is 1 atmosphere, and therefore the total pressure inside the balloon must be 1 atmosphere. Okay, so here we calculate mole fraction first. And then total pressure, which is 1 atmosphere times 0.4. Okay, similarly, 1 atmosphere times mole fraction. So in this case, partial pressure is just equal to the mole fraction of each gas, because the total pressure is 1 atmosphere. Now, when the balloon float to the higher elevation, the total pressure will become less than 1 atmosphere. And so if you are asked to calculate the partial pressure at a different elevation, then you need to know the total pressure, okay, because it's not 1 atmosphere. It may be 0.8. It has to be given to calculate the partial pressure. Okay, question number 6. We use a large beaker to collect 250 millimeter hydrogen in our lab. The atmosphere pressure is 102.4 kilopascal and the temperature is 25. So what we have is pressure, temperature, and volume. Okay, so we want to calculate how many moles hydrogen do we collect. So to calculate the number of moles of hydrogen collect, let's first explain how do we collect gas phase in the lab. So what we do is we have a water tank, and then we use a beaker full of water, and then we invert the beaker into the tank, so it becomes like this, and the water goes down. So this becomes vacuum inside because water goes away, so nothing inside beaker. And then there's a tube that contains hydrogen gas, comes in and placed inside the beaker. Now because hydrogen is lighter than water, so it goes up, okay, goes up and push all the water away. So eventually you have a tank, you have a beaker that has hydrogen inside, and the volume of the beaker is the volume of the hydrogen gas. So we want to calculate number of moles. So use ideal gas law, PV equals nRT. We have pressure, volume, temperature, so we can calculate number of moles. But one thing you need to take care of before we calculate this is that inside the beaker, because it's inside the water, so even though hydrogen goes in, push water away, water has a vapor pressure. So inside the beaker, the pressure not only due to the hydrogen but also due to the water vapor. All right, and so it's a mixture inside, and we have the vapor pressure is given 23.76 Torr as a partial pressure of the water. Now inside the total pressure is 1 atmosphere, and therefore from this you calculate the partial pressure of the hydrogen. So this pressure should use hydrogen partial pressure, which is 1 atmosphere minus the water vapor pressure. They have to be same unit. Okay, so here total pressure is 1 atmosphere, which is 102.4 kilopascal. All right. Sorry, it's not at 1 atmosphere. The given is 102.4 kilopascal. Or in this case, that's the atmosphere. And water vapor pressure 23.7, and therefore you need to change Torr to atmosphere or kilopascal. So the answer is 3.17 kilopascal. Okay, so Torr goes to atmosphere. 1 atmosphere 760 Torr, and then 1 atmosphere equals 101.325 kilopascal. So that gives you how much water vapor pressure. And then the pressure of hydrogen is calculated to be 99.23. And then use ideal gas law, PV equals nRT. We calculate number of moles. Okay, so here the R is 8.3145 because everything is SI unit. Okay, and the answer is 0.1 mole, or 1 times 10 to the minus 2 mole hydrogen.